very much, Emma. So mine is taking a very different turn now, I suppose, from the previous speakers, but obviously the computing knowledge that's been shared from the previous speakers will at least give some context for the models that I'm going to use. So though this is called a virtual field trip, it was virtual in the sense that we had to run these trips online because of the pandemic that we're all in. And I'm going to hopefully show you examples of how we used virtual outcrop models, so that's geology models, in both the Pyrenees trip and the Somerset trip. The Pyrenees trip is an 8-day long field trip, so it synthesizes lots of material over a relatively wide area. And I'll just show you an example of how we integrated the use of these models in one day of that trip. On that trip, we used three different virtual outcrop models. And the second trip is a shorter trip. It's onto the South Bristol Channel coastline in Somerset, a little village, well, near a small spot called Kilve. And it's only a 2-day trip, and it's very closely integrated with a taught module, which is on how to interpret or work with faults and fractures of rocks. Now, these are MSc level field trips. So the students already have a lot of knowledge, or at least experience, in how to collect data in the field. So that's not the primary objective in these trips. And also, I didn't build any of these models. One of the co-leader, or the main leader of the Bristol Channel, the Kilve field trip, I was involved in making their models because it was based on years and years of research. And the models we used were freely available from our colleagues. There's been a lot of sharing in the geological community because we've all had to sort of suddenly ramp up and do field trips remotely. And they were, feeding back to what's been said by the previous two speakers, they were actually built for research purposes. So people in geology have been using some of this technology for quite a long while in research purposes. And indeed, Abby mentioned this use of immersive environments in geology in oil companies, and I have used in those early hives where we went in and immersed ourselves in subsurface data. I've had some experience of working in those environments. So I'll go forward. In my next slide. So actually, I've said all of this. So this is some information about where the models came from. So I've just included this so that people can go back and find that information if they require to later from the PDF of this slide. So just to explain a bit about the teaching resources. So we did not run these, as I've explained, the courses weren't run entirely in a virtual world. That's not what we were trying to do at all. So it was augmenting or adding to traditional methods. So we had PDF slide packs, which had the field guide material in it with briefing and task instructions. Everything was run live on Teams. So we taught all day from 9 in the morning till 5 in the evening, as we would have done in the field. So we did our briefing live, and then everything was very much task-based. So all the data required for the exercises were within the field guide, or the PDFs, photos of observations or data from observations the students would have collected themselves, though they actually collected a lot of data themselves from the imagery and things that we used. So in terms of virtual material, now I know you wouldn't think of photo panoramas as virtual material, but in fact, if you're working in the mountains and you want to look at large cliff faces and collect information from it, having detailed photographs stitched together and ortho-rectified provided a really valuable resource and helped us. Actually, we're better than trying to stand in the field with binoculars and worrying about vegetation and shuffling students along to get viewpoints. The other thing that people maybe sometimes forget about that exists as a resource is Google Earth. And it's stupendous for geology in mountains because, the geology can be exposed in the fabric of I suppose the digital, the terrain models in Google Earth give us that the structure of the geology beneath the surface. And what I do a lot is overlay maps, which helps bring the three-dimensional aspect of the geology into the classroom for the students, because you can travel and see it and stand on mountains and look, there's a fault, there's a fold. And then obviously, as I mentioned, we use these models. We had more models for Somerset. In fact, the whole area is covered with this drone imagery. And in the end, though there were 6 models available, in the time we had, we only managed to use about 3. So let me move on. So the first example comes from Spain, the Ainsa Basin. And this one day, we were interested in characterizing deep water slope channel deposits. So I realize this is technical, but essentially we have turbidity currents that come down off the shelf, carry sediment down the continental margin into the slope environment, and they cut into the underlying sediments and build stacks of sand, which is porous material, which provides good reservoirs for oil and gas, and also for perhaps putting in CO2 back into the ground in depleted reservoirs. And parts of the aspects of the students need to know how these features look like, to translate that information into looking for resources in the subsurface where you can't actually see these features, and also the processes involved in sedimentology, how the individual events, how the beds of sand were laid down, because that gives us other information. So as I mentioned, we had these high resolution photo panoramas, and this has actually 4 or 5 of these stacked channels. We use Google Earth as well in this area. Then we have this virtual outcrop model of a quarry, a disused quarry. Lots of detail, students could make measurements, and then we also had to augment this, however, with field photographs of the details that you couldn't see. So you had to add information from, that you already had from real world into this virtual outcrop model. So just to then show you what you might do with geological maps. So this is a geological map, lots of detail. The different colors represent different sandstone layers. The one we were interested in is this yellow layer that curves around here and continues on here. So why does it curve? Why is it exposed just in those locations? And if I overlay it, and I've actually changed north slightly on Google Earth, you can see that this yellow layer we're interested in actually is on the top of a little cliff. You can see it from the other side of the river or along the road. It extends for about 2 kilometers in length. And this is the one we have our own detailed photo panoramas, and that colleagues have taken drone imagery and built into a 3D model. Then you can see that you go down further along the road, you find the quarry, and we also had borehole data from behind the cliff face. So the students can see the context. If we were in the real field, you would travel to these places, but you can actually see where you're going. Also, you can understand why these rocks are bent around like this, because they're curved in the landscape. So it's actually folded, which is important for another whole component of the course, which I won't talk about now. So just to let you see then, hopefully this is going to work, show you one of these virtual models. So this is this channel, one individual channel that we want to look at. It's got a margin where the sands are thin. It's got an axis where the sands are thicker. And normally the students will go into the quarry and they'll try and make sort of virtual, or 1D transects or logs through the outcrop to actually build up some quantitative information about how these sandstones are organized into the body. So now we're going to look at one of these models. So here we go. So this is the 3D model, which I can spin around and do all sorts of things about. So again, to orient you, this is the channel margin, this is the channel axis. So the students can zoom in as though they were walking down the quarry. They can make a screen grab and they can make a log of what the sand bodies, how they're stacked in this part of the model. They can then walk further along the outcrop. So to go into the center of the channel, again, they can maybe screen grab part of it, make measurements of how you've got thicker sands, more sand here, thinner sands up here with more mud. And they can then actually go and zoom in and see the details of how those beds are organized in more detail. So you have, for example, here a sandstone bed that's about 30 centimeters thick, and as you move to the left in the image, it disappears all the way away, and that tells us that this next sandstone bed came in and eroded the underlying bed, and that tells us information about how these sands were deposited. And you can zoom right in. Now, I haven't put the quality as the highest because I'm conscious of the bandwidth we're using today, but you can see details of how this individual bed here has different components within it that you can actually see. So to show you an example, and they would spend, well, we would normally spend 2 hours in this quarry. So the exercise we gave the student involved all this material. They worked in groups in separate channels within teams, and did all the exercises in about, again, a couple of hours probably by the time we did the briefing and the discussion afterwards. So to go back to my PowerPoint slides now. This is an example of the sort of one example of output that the student generated. So here, one student generated, or one team actually. This was their channel axis, where you could see the frequency of the sandstone beds, some idea of the grain size. This is the idea of the channel margin. And this is a very conceptualized sketch of how this might be summarized, and a model you could use as an analog for the subsurface. So that's an example of how we integrated using a virtual outcrop model into a whole day of field teaching. So now we'll move quickly to Somerset. Here we have these colleagues of mine drone the seafloor, not the seafloor, sorry, the shore face, the wave cut platform, the vertical cliffs, spliced them together and added in photographs. And these were all built with Agisoft software, and they're freely available on Sketchfab. Now this course focuses on learning about faults and fractures. Now this is a classic example of a sort of casebook fault here. So you can see the beds of rock, limestone beds, and hard white. In between, softer receding beds of shales, two different types of shales actually. And then hopefully you can see that these beds that are continuous here stop sharply against a surface which has again some material veining along it, and then you have a different set of rocks here, and this block has actually moved down relative to that block, and so you actually have a fault along here. So what the students exercise here is to learn how to systematically characterize a fault. So they need to collect geometrical data from around the fault. Now to do that, we had to give them orientations and some dips on the beds, and they obviously have to have some scale information, which we provided by photographs. But then the rest of the information they can glean from using the model. They need to get geometrical information, data from the actual core of the fault zone to understand something about the kinematics, that's how the fault moved, and then more information to integrate to understand about the mechanics, so we understand why and how these faults form, and then elements of fluid flow. So I just want to again show you this model. So we're going to go back to here, we're going to go to kills. We're going to go into full screen mode. So hopefully this is visible. So again, I can tilt around the model. It's incredible resolution. It's absolutely amazing. So we can zoom right into that fault and look at the shape of the beds as they intersect the fault surface. We can look at the limestone and the calcite veining, which indicates fluid flow along the fault. Now you can imagine in the feed, you've 35 students crowded around this bit of outcrop. There's a little rucksack for scale. There's not going to be much space, is there? Everybody's going to be jostling. So because, you know, in the real world, this fault actually continues around to the other side of this little outcrop. So you can just move around and take half the group over to the other side and divide them up. Now, obviously, when they're working in the virtual world in their groups, they can all get to look at the whole thing. And again, you can zoom right in, we can make measurements. They know the orientation of this surface. They can go in and see there's actually veins right up on the fault plane itself. And if you look at the veins, sorry, I was trying not to make you seasick. You can see some striping down those vein surfaces, and you can imagine as one fault block moves over another, it sort of scratches, and actually veins grow in the orientation of the fault movement. And so by measuring these, you get an indication of the kinematics or how the fault is moved. So a lot of fabulously detailed information that we can glean from these data sets. Now, the last thing I want to show you, just looking at my time. Yeah, have I run out of time?
It's okay, we can give you a couple more minutes.
Well, yeah, okay, sorry. It's very quickly. So the last thing that we saw was you can see on these surfaces here how the faults, the beds are fractured or have lots of jointing. So the last example is just to show you how the students worked with those data. And so this just is actually to show you can make real measurements. So this is, again, a part of the drone image, and this bed, which is exposed on the foreshore. You can see lots of joints fracturing. We divide it up into subsections. The students then use those images. They can look at the drone, but it's easier to actually look at the still image that we've captured from it. They can make measurements. work out the different sets, work out their orientation, sizes, etc. So to summarize, we would ultimately say that these virtual outcrop models, and Google Earth I would include as a free resource of such, are a valuable part of the toolkit for teaching online geology field trips. But they're addition to the resources we already had. We couldn't have run our trips without all the existing exercises, teaching materials, and field guides. So as was mentioned by the previous speaker, it enriches the experience, that makes it more enjoyable, and allowed the students to collect and measure data with a feeling that they were there in the world, and provides the basis for improved exercises from our perspective. And again, as mentioned again by the previous speaker, it allows access to inaccessible areas. So by having the cliffs that you can't actually climb up on, even in the quarry, you can use this. It also is helpful for bad weather, poor lighting, problems that we have in Spain, and in Somerset, particularly the tides. We normally only have about 4 to 6 hours to work on that wave cut platform. Now, the negatives, which of course you can mitigate against in the real world when we're back in a classroom, is that you require higher and stable bandwidth. And that was a problem with the students. So we had to have a backup, which was using screenshots from the VR models. Now, and then my final last point really was that it's clearly a rapidly developing area, as the previous speakers have shown. And colleagues of mine have built entire undergraduate field trips in a virtual reality world using the Unity gaming platform. So the students have actually gone in without headsets. We don't have that capacity, and actually moved around with an avatar explaining the geology for them and learning basic techniques. But ultimately, the consensus of most of the staff is that nothing replaces doing geology in the field. This is obviously a cheaper, perhaps, way of doing it. It took us a huge amount of preparation time, though. But obviously, the future, you might think of ways of combining the two components. So if you could, take iPads in the field, probably not a good enough bandwidth, but you might work in a classroom for part of the day, a couple of hours, look at the virtual material, and then integrate it with what you're doing in the field. Anyway, that's just a